Hi everyone, I'm Miyang Lee. I'm a rising senior at the University of Michigan.
Hi, my name's Priscilla Nguyen, and I'm a rising senior at the University of Texas at Austin, and I'm here for the summer with the Summer Research Opportunity Program.
Yeah, we are now working on a project about a new kind of concrete material called ECC. So what's so unique about ECC is that it's not only good at compression, but also good at tension. So trying to use this special quality, we kind of want to design small structures, small joint to connect different pieces of ECC elements, just like Lego blocks, so that we can use many of them to build up real big structures. And also, Professor Lee set up some rules, some criteria for this kind of joint. That is, it should be easy to assemble, easy to disassemble, and also be able to reconfigure.
And the reason we are focusing on this is because a lot of material goes into the waste landfill once the structure has met its service life. This gives us an opportunity to reuse the materials, and with that, reduce the use of raw materials and reduce the energy consumption that requires to make these new materials.
Yeah, and it also save a lot of energy and human labor costs and stuff like that. So I'm just gonna talk a little bit about my design first. So I use an aluminum tube at the middle to connect two pieces of VCC elements using bolting techniques. And the idea behind my design is that I would like the metal joint to hold the most severe tension at the middle part at the bottom from the bending force. So this is kind of easy to assemble, easy to disassemble, and definitely after pulling out the screws, you can easy to reconfigure it. So we did some tests on this joint, and the test result can be shown on the screen. And you can see that the two dashed lines stands for the two continuous beams, and the other four stands for my joint design. So this is a stress versus stroke distance graph. So basically, the joint design absorbs more energy before failure compared to the continuous beams. And also, I observed that the cracks basically happen right at the screw holes actually. And also, the aluminum joint very deformed, which is not so desired for my design, because I would like them to deform a little bit just to give some curvature both inside and outside.
About my design, I got a lot of help from Young in his observations. He observed that because of the thickness of his joint, it wasn't able to deform. And so what I did, I actually used only plates instead of the whole joint covering all four sides. So this is a reason for this is to allow the plates to deform with the ECC material. Also, I used a thinner plate because, like I mentioned before, the joint that Mingyang used didn't deform as much as you had wanted, and so my plates were able to deform a little bit more. The thickness that I used half of his, which is 1/16 of an inch. Also, my plate was 3 inches long, and this is because I'm using 2 screws on each beam to connect the plates, the top and bottom plates, to the beams. This clip is just about me and my mentors mixing, and we're preparing the ACC mix. As you can see, the ingredients shown and include cement, fly ash, water, super plasticizer to help make the fresh ECC mix more flowable and not just be hard to pour into the molds. Okay, now we'll be talking about the results and observations I made from my specimens. The first graph shows the stress versus displacement curve for the continuous beam. The continuous beams acted as control specimens in this project. The dashed lines represent the specimens that were tested with the MTS 810 machine. The solid line represent the specimen that was tested with the instrument machine. As you can see, the continuous beams were able to sustain between 12 to 15 megapascals of flexural strength, or had that amount of flexural strength, and a displacement up to 9.5 millimeters. This next graph is the stress versus displacement curve for the joint beam specimens. The specimens were able to sustain between 5 to 8 megapascals of flexural strength. As you can see, this is the flexural strength for the joint beam specimens was quite lower than the continuous ones, and the displacement achieved was up to 8 millimeters. Even though the specimens didn't sustain as much load as the continuous beam, it still shows the ACC was exhibiting its unique property to carry load even when cracks began. So this is known as strain hardening. This image is a typical failure of the joint beam specimens. As you can see, failure cracks are located where the aluminum plate came into contact with the ACC beam, so there are still compatibility issues between the two materials. Also, the cracks were usually on the outer screw holes, and would seem to begin from one face of the ACC beam and where the screws were located. So, interesting enough, we found that for both of our designs, our joint beams actually fell near the connection. So I think in the future, if we wanted our designs to succeed, we should design the joint in a way that the cracks don't propagate from the connection, but from other parts of the beams.
Yeah, and also we found that the failures from both of our designs are basically right at the screws, which means that the stress concentration is still a really big issue for this kind of connections. So we might want to see whether different kinds of joining techniques may work to help this, or maybe we can just choose another type of materials as screws to avoid, or to at least to not make this situation worse.
Also, we are considering maybe using bigger specimens in the future, maybe have them be wider a little, instead of 1.5 inches wide, make them 3 inches wide. We think this can help create multiple cracking. Multiple cracking is desired in ECC because that allows the material to gain strength while the loading takes place.
Yeah, anyway, so we still think there's a lot more way to go before we really achieve our project goal to build up a joint that acts just like the Lego blocks. So we hope the future teams, so people can do better than us. Yeah.
Thanks for watching.
Thanks.